So in the previous class, we were talking about a counter design problem. You guys decided a counting sequence for this 3-bit counter, and the desired sequence was 5, 4, 3, 2, 1, 7, 0, and then back to 5. So that pattern keeps repeating. Uh, a few things to note here. One is that it is going in a very arbitrary sequence. So this is as long it's a 3-bit counter, so it can only have states between 0 and 7, but those states appear in a very random manner. So it's an arbitrary choice for the sequence. That's one thing to note. The second thing to note is that we are actually skipping a state here. We don't have 6 being counted by this counter. So how do we go about designing this counter? And we also picked JK flip-flop to do this. We could have picked a D flip-flop to do it. We could have picked a toggle flip-flop to do it. But we picked a JK flip-flop to do it. So the first thing that we did was we drew a state diagram for which we used circles to indicate states. In this case, we have 7 unique states. So we drew 7 circles. And then we used arrows to indicate the state transitions. So one state to the other. So when we did step 1, the state diagram looked something like this. So if you start at 5 here, we indicate the state by writing in binary the 3-bit output of the counter. And then we went from 5 to 4 to 3, 2, 1, 7, 0, back to 5. So using the arrows indicating state transition and the circles indicating the states. And in fact, we can add on some more information on this. For example, I can call this, say, state 0 and state 1 and state 2 and state 3, state 4, state 5, state 6. I don't have to use the bit value, so I don't have to call this state 5, state 4, and so on. This is an arbitrary choice because I'm just naming those states. So typically in a state diagram, you will see S, capital S, being used to indicate state, and then the subscript being used to indicate the number of that particular state. So right away, you know that we have seven different states involved in this state diagram, and we are using the arrows to indicate transition. And when does it transition from one state to the other? Well, when you have the active clock edge, right? So transition happens. Transitions happen when there is an active edge on clock. So what are we going to use? We are going to use multiple flip-flops, and we are going to tie all the flip-flop clock inputs to one timing source. And when there is so I could have designed a positive edge triggered counter, or I could have designed a negative edge triggered counter. I think we decided to do a positive edge triggered. And if that is the case, all the flip-flops are in sync with one clocking source. So when there is a positive edge on that clocking source, there will be that transition from one state to the other. All right, so that was step 1. Step 2 was, by the way, if it's a 3-bit counter, we need 3 flip-flops to do it. And the output of the flip-flops, that's what indicates the value of the counter. So because we have 3 values here, as you can see, 101, 110, 011, and so on, we would need 3 flip-flops to give us those 3 outputs. And if this is, let's call this, if this is, say, Q0 and Q1 and Q2, the output of the flip-flops at that time, then using our terminology, I can say this will be Q0 plus and Q1 plus and Q2 plus, right? The next state. as far as just the first two states are concerned. And that applies for all the states here. There will be a current state and then there will be a next state. Okay, so the next the next step actually was to draw a state transition table. So what we did was in the leftmost column, I used ABC. So I should probably change this quickly as well. So if I use numbers, it'll be easier to keep track of which one is least significant and which one is most significant, but it doesn't really matter as far as design is concerned. QC, QB, QA, and I'm using QA to be the least significant. Coming back to this slide, now you have the current state, the current value of the counter, whatever the flip-flops are providing at that particular time. Then you have this transition to the next state after the active edge of the clock. And what we are going to find out is using the excitation tables of the JK flip-flop, because that's what we are using to build this counter, we are going to figure out what should I give to the most significant flip-flop C, flip-flop C. The inputs are JC and KC. Flip-flop B, inputs are JB and KB. Flip-flop A, inputs are JA and KA. So what should I give at these inputs so that there is a transition from Qs to Q pluses? So for example, if I look at JC and KC, how do I figure out the inputs there? Well, I have to observe QC and QC plus. QC goes to QC plus. And for each row here, 0 is going to 1. If I want the output of the flip-flop to go from 0 to a 1, using the excitation table of the flip-flop, I need to provide 1x at the input for JC and KC. And in a similar manner, based on, let me do this. Let me box things up. Depending on QC and QC plus, the transitions between QC and QC plus, I can find out JC and KC. This is simply by looking up the excitation tables of the JK flip-flop. And similarly, I look at QB and QB plus to find out JB and KB, the inputs to the flip-flop B. And I look at QA and QA plus to find out JA and KA. Looking up excitation tables, but many times. So a lot of repetitive work, but not difficult at all. Now, how did we write the current state? For current state, we just wrote all the states of the flip-flop, of all the states of the counter, 0, 0, 0, all the way down to 1, 1, 1. All the 8 states of a possible 3-bit counter. We did not do this leftmost column for current state. That has nothing to do with the counter that we are designing. Well, only a little bit. It is a 3-bit counter. That's the only thing. But the next state column, that's what is crucial, because that is dictated by the counting sequence that we pre-decided. That was the 5, 4, 3, 2, 1, 7, 0. Now, after 0, 0, 0, what did we have? Go back and take a look. After 0, 0, 0, right here, we had 5, 1, 0, 1. So we filled up 5 there, 1, 0, 1. And similarly, after 1, we had 7. After 2, we had 1. After 3, we had 2, and so on. That's how we filled the current state and the next state. And then using the excitation tables, we filled JC and KC. Now, my next step is going to be to figure out the 6 equations for JC, KC, KB, all these guys, JC, KC, JB, KB, JA, KA, in terms of QC, QB, QA. Those are the 3 outputs of the 3 flip-flops. So let's try to do that. So for that purpose, I'm going to copy this guy from here and let's see. Yeah, that was step 6. So to use this to find those equations, and I will try to do that over here. So I'm going to use this guy as a reference here, and let us try to do not for everything because it's going to be repetitive. I will just do it for I'll just start doing this for one of them. So let's see. I need a K-map for JC. So let me make the K-map here. This is going to be a 3 variable K-map. One, two, three, and I've got that here. Let me move this down. Give this 0, 0, 0, 1, 1, 1, 1, 0, 0, and 1. My inputs are current state QC, QB, QA. So QC, QB on the columns and QA for the rows. Next, I fill out 1, 1, 0, 0, 1, 1, 0, 0, and then all X's. Right. So that's for JC. Now I'm going to also quickly do this for others. Copy, paste, paste. I think I got 5 here. Oh no. All right, let's do the other one at the end. All right, so for JCKC, all right. And I'm going through this long process just because I have the next step requires me to do this. So that's why I'm going to this repeated work. All right, so I have a K-map for JC. I can combine the ones. So I'm going to go for the simplest implementation. For the simplest implementation, I would simply have what would be the equation for JC? I would simply combine these two with these two, right? That would be the simplest. And that would mean that my JC equals, what would that be? QB complement, I think. Right, that's it. Now, if I come down here and go to KC, what would be KC? KC would be 4x's and then 10x1. Right. Now I start combining the ones. How should I combine the ones in this case? I think the best way to do this. Oh, by the way, I hope you see that there are multiple ways of doing this, right? They could be multiple ways of implementing KC because the simplest expressions are not unique. So the counter design process can go in multiple ways. So you may get different answers is what I'm trying to say. So for this one, my no, it's probably this. And for this one, my best bet is right here. So those two groups. So what is my KC? KC is going to equal QA complement, or let's see, QB. Next, let's do it for JB. For JB, in my table, I have 01XX, 01XX, 10XX, 10XX. All right, so for this guy, what would be the combination? I guess this one can only be combined with this guy, and this one can only be combined with this guy. So that would give me JB. What would that be? I have QC and QA complement, or QA and QC complement. All right, so this is in a very nice form actually. What is that? QC exclusive or QA. So I can simply write that. That was for JB. Now let's go for KB. XX10XX X1. Okay, I believe the two groups will be this and this, giving you KB as QA complement or QC. Next is JA. All right, who picked JK flip-flop? T flip-flop would have been so much easier. We would have had to do this 3 times. I am kidding, of course. JA is 1x, 1x, 1xxx. All right, so this is pretty easy. Can somebody help me figure out what is JA? Simplest equation for JA? Yes, 1 is right, because I can combine everything. Next, I think I'm left with just 1, right? So that particular one, I will just do it here. Current template after. I think I had it saved, yes. And this will be JA, which is the last one. Sorry, KA is the last one. What would be KA? X0, X1, X0, X1, X1, X1. All right, so for this guy, what would be the groups? Let's see. I think the best way to do this would probably be that and that. So this will give me KA as QC or QB. All right, so I hope you have seen that we were able to get all the equations for the inputs, right? Now in terms of sketching, this is how you would sketch. first thing, you would draw the flip-flops out, right? So first thing, you draw the flip-flops, which means you have drawn 3 JK flip-flops. And because I like to see the most significant flip-flop on the left and the least significant flip-flop on the right, that's how I'm going to arrange it. And I now have figured out the combinational logic, so I'm going to erase this. I've figured that out. I'm going to erase these question marks because now I know them. I've made all the flip-flops positive edge triggered, and I have tied them into a clocking source because I wanted this 3-bit counter to be a positive edge triggered counter. Next, I just need to provide the inputs, right, based on the equations that I figured out. And those equations are based on the simplest SOP implementation, right? So I'm not taking care of hazards, static hazard. I'm not taking care of any of those. It is the simplest expressions. What is JC? Based on the equation, JC equals QB complement. How do I do QB complement? I'm going to say use blue here, and I'm going to get QB complement and go into JC, right? The best way probably is this. So that would be QB complement going into JC. Next, KC equals QA complement or QB. So I'm going to simply do this over here. I'm going to draw an OR gate, and I'm going to indicate 2 outputs so that doesn't get very messy. And I'm going to indicate that JC no, it was KC. KC equals QA complement or QB. KC is QA complement or QB. Those guys are coming from QA complement is coming from here, and QB is coming from here. Right, so I would take those 2 wires and go into an OR gate, and then the output would essentially connect to my KC input right there. And this process will continue. You will have more and more gates going on, and you will complete all these inputs. So you still have to at least sketch. You know it, but you have to sketch it for JBKB and JAKA based on the equations that you drew. But after you draw all of that, that would be the counter that we desired. That would be it. That would be the answer. Now, one question that we can ask here is this. So I'm going to title this Random Powerup State. So the question that we are asking here is, what if this counter, this 3-bit counter, randomly powers up with value 6. So I know that I actually skipped over this, right? So this is one of the skipped states, I actually didn't even use this. So if it randomly powers up at 0, 1, 2, 3, 4, 5, 7, I know how it is going to run. Because if it randomly powers up in one of these states, then I know it's going to stay in this loop. If it randomly powers up at 3, it will go to 2 next and it will be in this loop. The question is, what if it randomly powers up in a completely different state, which is 1, 1, 0? What happens then, right? Where does it go? Right, 6. Does it go into the loop, right? Does it go to 0? Does it go to 7 next? Does it go to 4 next? Or does it never go inside these transitions? What happens if it randomly powers up in this skipped state? That is the question. So we have to kind of backtrack, because we should be able to answer this, right? Because we have already implemented the counter. It is done now. We know how it looks like. It is the simplest SOP expressions and the flip-flops. So once we have figured that out, we should be able to answer, because we have made it now. Once we have designed it, we should be able to answer what happens if it randomly powers up at the skipped state. And there are many possibilities, right? So depending on your design, it is very possible that so there's no good way of knowing what it does after this. It is very, very dependent on the simplest SOP expressions. And it's not even unique, right? So depending on which one you choose, your behavior of the counter might differ. But I want to go through the steps of figuring out what happens in our current implementation. So 6, okay, so my question is this, right? 6 was XXX. After 6 comes XXS. I didn't know that. So I used all these guys. So you see, I'm going to highlight the things I'm concerned about. I'm concerned about that right now. What happens after I get 6? I just labeled it don't cares. But remember, don't cares in the K-map, when you use the don't care in a group, it will count as 1. And if you leave it out from the group, it will count as 0. So I need to figure out what those specific what those specific don't cares, how did we use them? Did we use them in the group or did we not use them in the group? And this is all with respect to QC1, QB1, and QA0. So let's try to figure that out. Go to the K-maps, and this is why I actually drew out all the K-maps. And take a look at which cell corresponds to 6. QC has to be 1, QB has to be 1, QA has to be 0, right? So that was, I'm going to indicate that in pink, for maybe green, right here. And right here, right? That is, that particular cell is the one that we are interested in observing. So now let's see. In the first one, I left out that don't care in the I didn't group it. So that counts as a 0, right? Right there. That counts as a 0. What does that mean? I will go to, well, that counts as a 0. How about this guy? This is in the group, so this counts as a 1, right? Next, JB in the group counts as a 1. KB in the group counts as a 1. JA in the group counts as a 1. And the last one, right here, counts as a 1. So it seems to me that everything is counting as a 1 except for JC. So what should I do? Well, I should do this, right? I should go back to my table. Perhaps erase these. I don't need that. And I should change all these JC and KC values to 0, 1, 1, 1, 1, 1. Because that's how I have implemented it. Now, I know the current state, I know the J and K values, I should be able to figure out the next state. So I'm going to also erase the next state, and I want you guys to tell me what QC plus is going to be. What is QC plus? QC is 1, JC, KC are 0, 1. What is QC plus? Jump and kill, JC 0, 1. JK flip-flop can be in jump state, kill state, store state, and toggle state. Low, 0. 0 is right. It is going to be 0 because you reset it, right? 0, 1. You killed it. All right, next. JB, KB is 1, 1. Which state are we in? If JB and KB are 1, 1, which state? Hold, hold, set, reset, toggle. Which state are we in? Toggle. Absolutely right. 1, 1 is toggle. So QB was 1, it will toggle to 0. Yes, beautiful. How about the last one? JAKA. 1, 1. That means toggle state. So QA will become 0, 2, 1. Very nice. So now let's answer the question. What happens when this particular counter randomly powers up at 6? After 6, how is the counting pattern going to be? Now we have figured it out. It is actually going to go to 1, right? So using this, I can complete my state diagram. So it looks like it is going to go from, let's see, blue. All right. So from 6, it's going to go to 1. And this is dependent on how we have implemented how we have implemented this counter. And there's no way to know this, right? Until I actually did all the K-maps, there was no way for me to figure this out, which is why I did all of that. So how is the counting sequence going to be if it randomly powers up at 6? It will go from 6 to 1 to 7, 0, 5, 4, 3, 2, and it will be in the loop after that, right? Sometimes, if there are more than one skipped states, so suppose the skipped states were 6 and 0, it is very possible that if it randomly powers up at 6, it will go back to 0 and then back to 6, back to 0, back to 6, and it will never come in to the cycle of counting. That is also possible. So there are many, many possibilities that can happen depending on the way you implement those functions. Questions about the counter design process and how we deal with the random power-up states. All right, so while you guys are thinking of questions, let me also ask you this. Is it possible that, suppose as a designer, I say, if it randomly powers up at 6, I want it to go to 3. Is it possible for me to design that counter? Yes, change the table. Absolutely. So if I want this to go from, instead of going to 1, if I wanted this to go to 3, all I would have to do is I would go back to the table here and I would have to change this to 3, right? 0, 1, and 1. And then JC, KC, KB, everything will change after that. So that is also possible. Next question. Is it possible for me to design this counter the 3-bit counter using 3 different types of flip-flops? What if is it possible for me to do, instead of using JK all the way, can I do this? Can I use T flip-flop here, a D flip-flop there, and a JK flip-flop there? Is that possible? It just gets confused. Well, we can take advantage of certain types of flip-flops, right? So for example, if you had D flip-flop, the characteristic equation for D is what? Q plus equals D. So, making up the tables here will become very, very fast. That will be very quick. But the answer is yes, it is very possible. All you have to do is, what would you have to do? You would have to change this to, instead of JCKC, you would change that to TC. Instead of JBKB, you would change that to DB. And JAKA would remain the same. And then instead of using excitation tables for just JK, now you are using excitation tables for T, D, and JK. But that is possible, right? It's possible for me to make my choice of flip-flops. I can have all 3 being different as well. Okay, so let's go on here and erase this and this and this. And it looks like you guys don't have any questions at this point. So I'm going to stop recording for this particular lecture.